Hello and welcome. Tonight we're going to embark on something remarkable. We're going to travel farther than any human being has ever gone. We're going to leave behind everything familiar, our cities, our planet, our sun, and venture outward into the vast cosmic ocean. We're going to journey all the way to the edge of the universe itself, if such an edge even exists. And along the way, we'll discover things that challenge everything we think we know about space, time, and our place in the grand scheme of existence. Now, I know what you might be thinking. The universe is huge, almost incomprehensibly huge, and you'd be absolutely right. But that's exactly why this journey is so fascinating. Because in exploring the universe, we're not just learning about what's out there, we're learning about where we came from, what we're made of, and what it all means. But before we begin, please take a moment to like and subscribe, but only if you enjoy what I'm doing here. Also, leave in the comments where you're tuning in from and what time it is there. It's great to see how these videos connect people from around the world. Now get comfortable, dim the lights, and let's leave Earth behind and venture into the infinite. Let's start where we are right now. Earth, our home. A blue marble suspended in the darkness, spinning quietly through space. From here, standing on the surface, the universe seems almost calm. We see the sun rise and set. We see stars come out at night. Everything feels orderly, predictable, safe. But that sense of calm is an illusion. Right now, as you sit reading this, you're moving at extraordinary speeds. Earth is rotating on its axis at about 1,000 miles per hour at the equator. At the same time, we're orbiting the Sun at roughly 67,000 miles per hour. And the Sun itself? It's racing around the center of our galaxy at something like 500,000 miles per hour. Even when we think we're sitting still, we're in constant, furious motion through space. But let's begin our journey the way any great voyage begins, by stepping outside our front door. If we could rise up from the surface of Earth, we'd first pass through the atmosphere, that thin blanket of gases that makes life possible. The air gets thinner and colder as we climb higher. At about 12 miles up, we'd reach the edge of the stratosphere, where the sky begins to darken and the curve of the Earth becomes visible. By the time we reach about 60 miles up, we'd officially be in space. The air here is so thin it's almost non-existent. The sky turns black, and suddenly the Earth below looks small and fragile. What strikes most astronauts at this point isn't the emptiness of space. It's the beauty of Earth, our planet, with its swirling white clouds, deep blue oceans, and patches of green and brown land. Looks like a precious gem hanging in an ocean of darkness. There are no borders visible from up here. No countries, no divisions, just one world, alive and vibrant, floating in the void. But as beautiful as Earth is, we're not stopping here. We're going further, much further. The first major landmark on our journey is the Moon. Earth's only natural satellite sits about 239,000 miles away from us. That might sound like a lot, but in cosmic terms, the Moon is practically next door. It takes light just over a second to travel from Earth to the Moon. In fact, the Moon is so close that we can see it clearly with our naked eyes, and it's the only other world that humans have actually walked upon. Between 1969 and 1972, 12 human beings left their footprints on the lunar surface. They looked back at Earth and saw what we're seeing now, a beautiful, lonely world against the darkness. The Moon itself is a barren place. No air, no water, no life. Just grey dust, ancient rocks, and impact craters stretching across a desolate landscape. But the Moon is also important. Its gravitational pull creates our ocean tides, stabilises Earth's rotation, and may have played a crucial role in making our planet habitable in the first place. As we leave the Moon behind, we're entering a region of space that feels more empty. We're moving away from Earth's gravitational embrace, and the distances between objects start to become truly vast. This is where space really begins to feel like space. Out here, between Earth and the planets, there's mostly just vacuum, empty space. Or at least, that's what it seems like. But even in this apparent emptiness, there are things happening. Particles from the sun, charged electrons and protons, stream outward in what we call the solar wind. This invisible river of particles rushes past us at speeds of hundreds of miles per second. Sometimes, when these particles interact with Earth's magnetic field, they create the beautiful auroras we see near the poles. The dancing curtains of green and red light in the night sky are actually caused by solar particles colliding with atoms in our atmosphere. But we're not here for the solar wind. We're here to go further. And the next stop on our journey takes us to our planetary neighbours. As we continue outward from Earth, the first planet we encounter is Mars. The red planet sits about 140 million miles from the Sun on average, compared to Earth's 93 million. Mars has captivated human imagination for centuries. Even with our naked eyes, we can see its reddish glow in the night sky. And that red colour, it comes from iron oxide, essentially rust, covering the Martian surface. Mars is a cold, dry world. Its atmosphere is incredibly thin, mostly made of carbon dioxide, and the average temperature hovers around -80 degrees Fahrenheit. But Mars wasn't always like this. Scientists currently think that billions of years ago, Mars might have been much warmer and wetter. Evidence suggests it may have had rivers, lakes, and maybe even an ocean. Ancient riverbeds carved into the Martian surface tell a story of flowing water. And where there's water, there might have been life. That's why we've sent so many robots to Mars. We're searching for signs that life once existed there, or might still exist in some form beneath the surface. But let's keep moving. Travelling inward toward the Sun, we'd pass by Earth again, then encounter Venus. Venus is often called Earth's twin, because it's similar in size and composition. But that's where the similarities end. Venus is a hellish world. Its thick atmosphere, made mostly of carbon dioxide, creates a runaway greenhouse effect. The surface temperature reaches about 900 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure is 90 times greater than Earth's, and clouds of sulfuric acid swirl through the sky. If you somehow landed on Venus, you'd be simultaneously crushed, incinerated, and dissolved. Not a pleasant place to visit. Closer still to the Sun, we find Mercury. This small rocky world is the closest planet to our star, orbiting at an average distance of just 36 million miles. Mercury has no real atmosphere to speak of, so nothing protects its surface from the Sun's radiation or the impact of space rocks. The result is a world covered in craters, baking in the Sun's heat during the day, reaching temperatures of 800 degrees Fahrenheit, and freezing at night, dropping to -300 degrees. And there, at the centre of it all, is the Sun itself, our star, the source of almost all the energy that powers life on Earth. The Sun is enormous, about 109 times wider than Earth. If the Sun were hollow, you could fit more than 1 million Earths inside it. But it's not hollow. It's a massive ball of hydrogen and helium, heated to unimaginable temperatures by nuclear fusion occurring at its core. In the Sun's centre, hydrogen atoms are crushed together under tremendous pressure and heat, fusing into helium and releasing enormous amounts of energy in the process. This energy radiates outward, eventually reaching Earth as the light and warmth we depend on for survival. The Sun has been burning for about 4.5 billion years, and it's got another 5 billion years or so to go before it runs out of hydrogen fuel. When that day comes, the Sun will swell into a red giant, possibly engulfing the inner planets, including Earth, but that's a problem for the distant future. For now, the Sun is stable, steady, and life-giving. Standing here, metaphorically speaking, at the centre of our solar system, we can look around and see something profound. All the planets, all the moons, all the asteroids and comets, everything in our solar system is held together by the sun's gravity. We're all bound to this star, orbiting in a careful cosmic dance that's been going on for billions of years. But as impressive as the sun is, it's just one star among hundreds of billions in our galaxy. And our solar system? It's just a tiny speck in a much, much larger structure. But before we leave the solar system entirely, we need to venture to its outer reaches. And that's where things get really interesting. As we travel beyond Mars, we enter a region of the solar system that feels fundamentally different. The rocky planets are behind us now. Ahead lie the gas giants, massive worlds made mostly of hydrogen and helium, with no solid surface to stand on. The first of these giants is Jupiter. And when I say giant, I mean it. Jupiter is enormous. It's more than twice as massive as all the other planets in the solar system combined. This massive world sits about 480 million miles from the Sun, and it takes almost 12 Earth years to complete one orbit. Jupiter is so big that it creates its own miniature solar system. It has at least 95 known moons, including the four largest, Io, Europa, Ganymede, and Callisto, which Galileo discovered way back in 1610. One of these moons, Europa, is particularly fascinating. Beneath its icy surface, scientists think there's a vast ocean of liquid water, possibly containing more water than all of Earth's oceans combined. And where there's liquid water, there might be life. Europa is one of the most promising places in our solar system to search for extraterrestrial life, and future missions are planned to explore it further. Jupiter itself is a turbulent world. Its atmosphere is filled with swirling storms, including the famous Great Red Spot, a storm larger than Earth that's been raging for at least hundreds of years. Wind speeds on Jupiter can exceed 400 miles per hour. The planet's powerful magnetic field creates intense radiation belts that would be deadly to any unprotected human. But despite its violent nature, Jupiter also plays an important protective role. Its massive gravity acts like a cosmic vacuum cleaner, attracting and capturing asteroids and comets that might otherwise threaten the inner planets. In that sense, Jupiter might be one of the reasons life on Earth has been able to survive and thrive. Beyond Jupiter, we come to Saturn. Saturn sits about 886 million miles from the Sun and takes about 29 Earth years to orbit once. Saturn is most famous for its spectacular rings, those beautiful bands of ice and rock that circle the planet's equator. The rings are incredibly thin. Though they stretch for hundreds of thousands of miles across, they're typically only about 30 feet thick in most places. Up close, the rings are made of countless individual particles, ranging in size from tiny grains to house-sized boulders, all orbiting Saturn in a flat disk. Like Jupiter, Saturn has many moons. One of them, Titan, is particularly special. Titan is the only moon in our solar system with a thick atmosphere, and it has liquid on its surface, not water, but liquid methane and ethane, forming lakes and rivers. Titan's atmosphere is hazy and orange, and the surface is shrouded in mystery. Some scientists think that Titan might be similar to a young Earth before life arose, making it an important laboratory for understanding how life might begin. Continuing outward, we reach Uranus and Neptune. These are the ice giants. Both are much smaller than Jupiter and Saturn, but still enormous compared to Earth. Uranus sits about 1.8 billion miles from the Sun. It's a strange world, tilted on its side so that its poles point nearly directly toward and away from the Sun at different times in its 84-year orbit. Scientists aren't entirely sure why Uranus is tilted like this, but it's possible that a massive collision long ago knocked it onto its side. Neptune, the farthest known planet from the Sun, sits about 2.8 billion miles away. It takes Neptune about 165 Earth years to complete one orbit. Neptune is a cold, dark and windy world. In fact, it has the fastest winds in the solar system, with gusts reaching over 1,200 miles per hour. Neptune's blue colour comes from methane in its atmosphere, which absorbs red light and reflects blue. Neptune also has a large moon called Triton, which is geologically active and has geysers that shoot nitrogen gas into space. Triton is unusual because it orbits Neptune backward compared to the planet's rotation. This suggests that Triton didn't form alongside Neptune, but was instead captured by Neptune's gravity at some point in the distant past. And beyond Neptune? Well, that's where things get even more mysterious. Out beyond the orbit of Neptune, we enter a region called the Kuiper Belt. This is a vast ring of icy objects, leftover debris from the formation of the solar system. The Kuiper Belt contains countless small worlds, some of which are large enough to be considered dwarf planets. The most famous of these is Pluto. Pluto orbits the Sun at an average distance of about 3.7 billion miles, though its elliptical orbit brings it closer and farther at different times. Pluto is small, smaller than Earth's moon, and it has a thin atmosphere that freezes and falls to the surface when Pluto is farther from the Sun. In 2006, the International Astronomical Union reclassified Pluto as a dwarf planet rather than a full planet, a decision that sparked much debate. But regardless of what we call it, Pluto is a fascinating world. When NASA's New Horizons spacecraft flew by Pluto in 2015, it revealed a complex, geologically active surface with mountains made of water ice, plains of frozen nitrogen, and a heart-shaped region that captured the public's imagination. But even Pluto isn't the edge of the solar system. Beyond the Kuiper Belt lies an even more distant region called the Oort cloud. The Oort cloud is thought to be a vast, spherical shell of icy objects surrounding the entire solar system. It begins roughly 2,000 times farther from the Sun than Earth is, and extends perhaps as much as 100,000 times Earth's distance from the Sun. That's almost halfway to the nearest star. The Oort cloud has never been directly observed. It's too far away and too dark. But scientists think it exists because of the comets we see. Every so often, a comet appears in the inner solar system, swinging around the Sun before heading back out into the darkness. Many of these comets seem to come from the Oort cloud, their orbits disturbed by the gravity of passing stars or the gentle tug of the galaxy itself. And this brings us to an important question. Where does the solar system actually end? Is it at the orbit of Neptune, the Kuiper Belt, the Oort cloud, or somewhere else entirely? One possible answer involves something called the heliosphere. The heliosphere is a vast bubble of charged particles blown outward from the Sun by the solar wind. It protects us from much of the radiation and cosmic rays coming from interstellar space. The edge of the heliosphere, called the heliopause, is where the solar wind finally runs into the interstellar medium, the gas and dust between the stars. NASA's Voyager 1 spacecraft crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. Both spacecraft are now travelling through the space between the stars, sending back data as they go. But even beyond the heliopause, the Sun's gravity still influences objects. The Oort cloud, far beyond where Voyager has travelled, is still gravitationally bound to the Sun. So in a sense, the solar system extends much farther than we might think, perhaps halfway to the nearest star. Speaking of which, it's time to leave the solar system behind entirely and venture into the space between the stars. When we think about space, we often imagine planets, stars, galaxies, but most of space is actually empty, or at least very nearly empty. The vast distances between stars are filled with something called the interstellar medium. This is an incredibly thin gas, mostly hydrogen and helium, along with tiny grains of dust. On average, there might be only one atom per cubic centimetre in the interstellar medium. To put that in perspective, Earth's atmosphere at sea level contains about 10 million trillion atoms per cubic centimetre. Interstellar space is empty in a way that's hard to comprehend. But this near emptiness is important. The interstellar medium is where new stars are born. In regions where the gas and dust are a bit denser, gravity can cause the material to collapse, forming vast clouds called nebulae. Over millions of years, these clouds continue to collapse under their own gravity, getting denser and hotter, until eventually nuclear fusion ignites in the centre. And just like that, a new star is born. As we travel through this sparse region, the sun behind us begins to fade. After a year of travelling at the speed of light, the sun would appear as just another star, bright certainly, but no longer the dominant object in the sky. After 4 years, we'd reach the nearest star system to our own, Alpha Centauri. Alpha Centauri is actually a system of 3 stars orbiting each other. The 2 brightest stars, Alpha Centauri A and B, orbit each other relatively closely. A third, much dimmer star, called Proxima Centauri, orbits the pair at a great distance. Proxima Centauri is the closest star to our Sun, sitting just over 4 light-years away. And remarkably, Proxima Centauri has at least 2 known planets. One of them, Proxima Centauri b, orbits in what scientists call the habitable zone, the region around a star where temperatures might be right for liquid water to exist on a planet's surface. Could there be life on Proxima Centauri b? We don't know. Proxima Centauri is a red dwarf star, smaller and cooler than our Sun, and it's prone to violent flares that could strip away a planet's atmosphere. But the mere fact that there's a potentially habitable planet so close to us, cosmically speaking, is remarkable. It suggests that planets might be common throughout the galaxy, and if planets are common, maybe life is too. As we continue outward from Alpha Centauri, we encounter more stars. Sirius, the brightest star in Earth's night sky, sits about 8.6 light-years away. It's actually a binary system, with a bright main star and a dim white dwarf companion. Farther out, we find stars of all types. Red dwarfs, which are small and cool, but incredibly long-lived. Stars like our Sun, mid-sized and yellow. Blue giants, massive and hot, burning through their fuel at a furious rate and destined to die young in spectacular supernova explosions. What becomes clear as we travel is that stars are not evenly distributed through space. They're organised into a much larger structure, a structure we call the Milky Way galaxy. The Milky Way is home, not just for Earth and the Sun, but for hundreds of billions of stars, along with their planets, moons, asteroids, and comets. The galaxy is a vast disc-shaped collection of stars, gas, and dust, held together by gravity and rotating slowly around a common centre. If we could step outside the galaxy and look at it from above, we'd see a beautiful spiral structure. The Milky Way has several spiral arms, long curved streams of stars and glowing gas, winding outward from a bright central bulge. Our solar system sits in one of these spiral arms, called the Orion Arm, about 26,000 light-years from the galactic centre. The Milky Way is enormous. From edge to edge, it spans about 100,000 light-years. To put that in perspective, if you could travel at the speed of light, it would take you 100,000 years to cross from one side of the galaxy to the other. And remember, nothing with mass can actually reach the speed of light. So in practical terms, the galaxy is unimaginably vast. At the centre of the Milky Way, hidden behind clouds of gas and dust, lies something extraordinary, a supermassive black hole. This black hole, known as Sagittarius A, has a mass equivalent to about 4 million suns, but despite its enormous mass, it's relatively small in size. The event horizon, the point of no return around the black hole, is only about 15 million miles across. That's less than the distance from the Sun to Venus. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. Supermassive black holes like Sagittarius A Sol are thought to exist at the centers of most large galaxies. They grow by consuming gas, dust, and occasionally entire stars that wander too close. As material falls toward a black hole, it heats up and emits tremendous amounts of energy, often creating some of the brightest objects in the universe. Our galaxy's black hole is currently fairly quiet. It's not consuming much material at the moment, so it doesn't emit much radiation. But occasionally, we see bright flares coming from the galactic center, suggesting that something, maybe a cloud of gas or an asteroid, has fallen into the black hole's grasp. Surrounding the central black hole is the galactic bulge, a dense concentration of older reddish stars. These stars orbit the center in a thick, roughly spherical distribution. Farther out, in the disk where we live, stars are younger and more spread out. The disk is where most of the galaxy's gas and dust reside, and it's where new stars continue to form. But the Milky Way isn't just stars and gas. Most of the galaxy's mass is actually made of something we can't see, something called dark matter. Dark matter doesn't emit, absorb, or reflect light. We can't see it directly with any telescope, but we know it's there because of its gravitational effects. When astronomers measure how fast stars orbit the galactic center, they find something strange. The stars are moving too fast. Based on the visible matter alone, the stars, gas, and dust, the galaxy doesn't have enough mass to hold itself together. The stars should be flying off into space, but they're not. Something invisible, something with mass and gravity, is holding the galaxy together. That something is dark matter. Scientists currently think that dark matter makes up about 85% of the matter in the universe, but we have no idea what it actually is. It's not made of atoms like normal matter. It might be some exotic particle that barely interacts with anything except through gravity. Figuring out what dark matter is remains one of the biggest mysteries in modern science. As we zoom outward, leaving the Milky Way behind, we can see the galaxy in all its glory. A pinwheel of light against the darkness. Hundreds of billions of stars, each one potentially with its own system of planets, countless worlds, and maybe, just maybe, other forms of life looking back at us across the cosmic void. But the Milky Way, as vast as it is just one galaxy among countless others. And that brings us to the next stage of our journey. As we pull back from the Milky Way, the first thing we notice is that our galaxy isn't alone. Nearby we see other galaxies, small ones, large ones, each a collection of billions of stars held together by gravity. The closest large galaxy to the Milky Way is the Andromeda Galaxy, sitting about 2.5 million light-years away. Andromeda is actually larger than the Milky Way, containing roughly 1 trillion stars compared to our 2 to 400 billion. Like the Milky Way, Andromeda is a spiral galaxy with beautiful spiral arms and a supermassive black hole at its center. Something remarkable is happening with Andromeda. It's moving toward us. Despite the overall expansion of the universe, which causes most galaxies to move away from each other, Andromeda and the Milky Way are on a collision course. In about 4 to 5 billion years, the two galaxies will merge, creating a single, larger galaxy. It sounds catastrophic, but galaxy collisions are actually relatively gentle events. The stars are so far apart that they'll mostly pass by each other without colliding. But the gravitational interactions will throw stars into new orbits, trigger massive bursts of star formation, and eventually blend the two galaxies into one. The Milky Way and Andromeda, along with about 50 other smaller galaxies, form what we call the Local Group. This is a gravitationally bound collection of galaxies spanning about 10 million light-years across. Most of the galaxies in the local group are small dwarf galaxies containing anywhere from a few million to a few billion stars. These dwarf galaxies orbit the larger galaxies like the Milky Way and Andromeda, held by their gravitational pull. Two notable members of the local group are the Large and Small Magellanic Clouds. These are small irregular galaxies that orbit the Milky Way. They're visible from Earth's southern hemisphere as fuzzy patches of light in the night sky. For thousands of years, people living south of the equator have known about these clouds, and they've been named after the Portuguese explorer Ferdinand Magellan, whose crew documented them during their circumnavigation of the globe in the early 1500s. From our vantage point above the local group, we can see that galaxies tend to cluster together. Gravity pulls them into groups, and these groups are just the beginning of a much larger cosmic structure. As we zoom out further, beyond the local group, the universe begins to reveal its largest structures. We start to see galaxy clusters, massive collections of hundreds or even thousands of galaxies bound together by gravity. The nearest major galaxy cluster to us is called the Virgo cluster. It sits about 65 million light-years away and contains over 1,000 galaxies. At the heart of the Virgo cluster is a giant elliptical galaxy called Messier 87, or M87. This galaxy is truly enormous, containing several trillion stars, and at its centre lies one of the largest black holes ever discovered, with a mass equivalent to about 6.5 billion suns. In 2019, scientists released the first ever image of a black hole, and that black hole was the one at the centre of M87. The image showed a dark shadow surrounded by a glowing ring of hot gas. Galaxy clusters are held together by gravity, but they contain much more than just galaxies. Between the galaxies, filling the space within the cluster, is hot gas. This gas is heated to millions of degrees and emits X-rays. In fact, most of the normal matter in a galaxy cluster isn't in the galaxies themselves. It's in this hot gas filling the space between them. And just like individual galaxies, galaxy clusters are held together by dark matter. In fact, dark matter dominates the mass of galaxy clusters. For every kilogram of normal matter in a cluster, there's about 5 or 6 kilograms of dark matter. We can map where the dark matter is by observing how its gravity bends light from more distant galaxies, an effect called gravitational lensing. But even galaxy clusters aren't the end of the story. Galaxy clusters themselves are organized into even larger structures called superclusters. Our local group, along with the Virgo cluster, and many other nearby galaxy groups and clusters, all belong to a supercluster called the Laniakea supercluster. Laniakea, which means immeasurable heaven in Hawaiian, spans about 500 million light-years and contains the mass of about 100,000 trillion suns. And here's something amazing. All the galaxies in the Laniakea supercluster are slowly moving toward a common point. There's a region of space hidden behind the plane of the Milky Way, where the concentration of galaxies is particularly high. This region, called the Great Attractor, is pulling our entire supercluster toward it through gravity. We're moving toward the Great Attractor at about 600 kilometers per second, even as the expansion of the universe carries us in other directions. Beyond Laniakea, we see other superclusters: the Perseus-Pisces supercluster, the Coma supercluster, the Shapley supercluster. Each one contains thousands of galaxies, organized by gravity into the largest structures in the universe. And when we zoom out even more, we see something truly remarkable. From the largest possible scale, the universe looks like a web. Galaxies and galaxy clusters aren't randomly scattered through space. Instead, they're organized into long filaments and sheets, separated by vast voids where very few galaxies exist. These filaments stretch for hundreds of millions of light-years, forming a cosmic web that spans the entire observable universe. Along these filaments, where matter is most concentrated, we find galaxy clusters. In the spaces between the filaments, in the voids, there's very little. Imagine a sponge. The solid parts of the sponge are like the filaments, and clusters, that's where the galaxies are. The holes in the sponge are like the voids, vast empty regions with almost nothing in them. This cosmic web structure tells us something important about how the universe evolved. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly. There were tiny variations in density. Some regions were very slightly denser than others, but overall, things were smooth and even. Over billions of years, gravity amplified these tiny differences. Denser regions attracted more matter, becoming even denser. Less dense regions lost matter to the denser regions, becoming even emptier. The result is the cosmic web we see today. This process is still happening. The cosmic web is slowly evolving as gravity continues to pull matter together. But there's something else at play too, something that's actually working against gravity, pushing the universe apart. We call it dark energy. In the 1920s, astronomer Edwin Hubble made a startling discovery. By observing distant galaxies, he found that they were all moving away from us. And the farther away a galaxy was, the faster it seemed to be receding. This could only mean one thing. The universe itself was expanding. This was revolutionary. Before Hubble's discovery, most scientists assumed the universe was static and unchanging. But Hubble showed that the universe is dynamic. It's growing, stretching, with space itself expanding and carrying galaxies along with it. If the universe is expanding now, that means it was smaller in the past. And if we go back far enough, there must have been a time when the universe was incredibly small, incredibly hot, and incredibly dense. This is the Big Bang, the moment when the universe as we know it began. The Big Bang occurred about 13.8 billion years ago. In an instant, space, time, matter, and energy all came into existence. The universe began as an unimaginably hot, dense point and immediately started expanding and cooling. Within the first few minutes, the basic elements were formed, mostly hydrogen and helium, with traces of lithium. As the universe continued to expand and cool, matter began to clump together under gravity, eventually forming stars and galaxies. For a long time, scientists assumed that the expansion of the universe must be slowing down. Gravity pulls matter together, so it should be acting as a brake on the expansion. But in the late 1990s, two teams of astronomers made an astonishing discovery. They were measuring the distances to very distant supernovae, exploding stars that can be used as standard candles to measure cosmic distances. And what they found was shocking. The universe's expansion isn't slowing down, it's speeding up. This discovery was so unexpected and so important that it won the Nobel Prize in Physics in 2011. But it also created a major mystery. What could be causing the expansion to accelerate? The answer, or at least the name we've given to the answer, is dark energy. We don't know what dark energy is, but we know it's there because of its effects. It acts like a kind of anti-gravity, pushing space apart. And dark energy isn't just a minor player, it's the dominant component of the universe. Scientists currently think that dark energy makes up about 68% of the total energy in the universe. Dark matter makes up about 27%. And normal matter, the stuff that makes up stars, planets, and us, accounts for only about 5%. So when we look at the universe, only 5% of it is made of matter we understand. The rest is dark matter and dark energy, two mysterious substances we can barely study and don't understand at all. As the universe continues to expand, driven by dark energy, galaxies and galaxy clusters are moving farther and farther apart. Eventually, in the far distant future, billions of years from now, this acceleration will have profound consequences. Galaxies outside our local group will move so far away that their light can never reach us. The observable universe will shrink. A future civilization living in our galaxy might look out into space and see nothing but darkness and the handful of galaxies in our local group. They might conclude that they live in a lonely, isolated universe, never knowing about the vast cosmic web that once surrounded them. But that's a problem for the distant future. Right now, we're still on our journey, and we're approaching the edge of what we can see. As we zoom out to the largest possible scale, we begin to approach the limits of what we can observe. Light travels fast, about 186,000 miles per second, but it doesn't travel infinitely fast, and the universe has only existed for a finite amount of time. This means there's a limit to how far we can see. The observable universe is defined as the region of space from which light has had time to reach us since the Big Bang. Because the universe is about 13.8 billion years old, you might think the observable universe would be 13.8 billion light-years in radius. But it's actually much larger than that because the universe has been expanding the whole time. The current best estimate is that the observable universe has a radius of about 46 billion light-years. This means the observable universe is roughly 93 billion light-years in diameter. Everything we can see, all the stars, galaxies, and cosmic structures, exists within this vast sphere. But here's the thing. The observable universe is almost certainly not the entire universe. It's just the part we can see. Beyond the edge of the observable universe, there's probably more space, more galaxies, more stars. We just can't see them because their light hasn't had time to reach us yet. And because the universe is expanding, some of that light will never reach us. There are parts of the universe that are forever beyond our view. So is there an edge to the universe? Not in the way we usually think of an edge. The observable universe has an edge, but that's just a limit on what we can see, not a physical boundary. The universe itself might be infinite. It might stretch on forever in all directions. Or it might be finite but without an edge, like the surface of a sphere, which is finite in size but has no boundary. Scientists aren't sure which is correct. When we look out to the farthest reaches of the observable universe, we're looking back in time. Light from the most distant galaxies has been travelling toward us for billions of years. When we observe a galaxy 10 billion light-years away, we're seeing it as it was 10 billion years ago, not as it is today. In fact, we're seeing it when the universe was only about 3.8 billion years old, not long after the first galaxies formed. The farthest objects we've detected are galaxies formed when the universe was only a few 100 million years old. These ancient galaxies appear as tiny, faint smudges in deep space images taken by powerful telescopes like the James Webb Space Telescope. They're remarkable because they show us what the universe looked like in its infancy, giving us clues about how galaxies formed and evolved, but we can see even farther back, to a time before galaxies existed at all. About 380,000 years after the Big Bang, something important happened. Before this time, the universe was so hot and dense that matter existed as a plasma, a soup of electrons and atomic nuclei. This plasma was opaque. Light couldn't travel far before being absorbed or scattered by the charged particles. But as the universe expanded and cooled, it eventually reached a temperature where electrons and atomic nuclei could combine to form neutral atoms. When this happened, the universe became transparent. Light could suddenly travel freely through space. This moment is called recombination. The light that was released during recombination is still travelling through the universe today. But because space has expanded so much since then, that light has been stretched to longer wavelengths. What was once visible light is now microwave radiation. We call this the cosmic microwave background, or CMB. The CMB is the oldest light in the universe. It comes from every direction in the sky, forming a faint glow that fills all of space. the CMB is remarkably uniform, with a temperature of about 2.7 degrees above absolute zero. But it's not perfectly uniform. There are tiny variations in temperature, about 1 part in 100,000, from one region of the sky to another. These tiny variations are incredibly important. They represent the density fluctuations in the early universe, the seeds that eventually grew into galaxies, galaxy clusters, and the cosmic web. By studying the CMB in detail, scientists can learn about the conditions in the early universe, the composition of the universe, and even the geometry of space itself. The CMB represents the farthest back in time we can see with light. Before recombination, the universe was opaque, so we can't observe anything earlier with telescopes. The CMB is, in a sense, the edge of the observable universe in time. But does that mean it's the edge of everything? When we stand at the edge of the observable universe, looking at the cosmic microwave background, we're seeing the earliest light that can reach us. But what lies beyond? The honest answer is that we don't know, and maybe we can never know. If something is so far away that its light hasn't reached us yet, and if the expansion of the universe means it never will reach us, then it's fundamentally unobservable. It's beyond the cosmic horizon, but just because we can't see something doesn't mean it's not there. Most scientists think the universe extends far beyond what we can observe. It might be vastly larger than the observable universe, or it might even be infinite. Some theories suggest that our universe might be just one of many. According to the idea of cosmic inflation, a theory that describes the earliest moments after the Big Bang, the universe underwent a period of incredibly rapid expansion, growing exponentially in a tiny fraction of a second. Some versions of inflation theory suggest that this process might create multiple separate regions of space, each potentially growing into its own universe. These universes would be disconnected from each other, each with its own laws of physics, its own properties. This is the multiverse hypothesis. It's important to note that the multiverse is highly speculative. We have no direct evidence for it, and it's not clear we ever could. But it's a fascinating possibility. If the multiverse exists, then our observable universe, as vast as it is, might be just a tiny bubble in an infinitely larger cosmos. Other theories propose different ideas about what lies beyond. Some suggest that space might curve back on itself, like the surface of a sphere, so that if you travelled far enough in one direction, you'd eventually return to where you started. Others suggest that the universe might have a more complex topology, with different regions connected in strange ways. The truth is, we're limited by what we can observe, and right now, the edge of the observable universe is as far as we can go. So here we are. We've travelled from Earth, through the solar system, past neighbouring stars, across the Milky Way galaxy, through clusters and superclusters, across the cosmic web, and all the way to the edge of the observable universe. We've journeyed through 13.8 billion years of cosmic history, seen the light from the earliest moments after the Big Bang, and contemplated what might lie beyond. What have we learned from this epic journey? First, we've learned about scale. The universe is unimaginably vast. Distances that seem enormous on Earth, like the distance across a continent or even to the moon, are nothing compared to the cosmic scales we've encountered. The distance from Earth to the edge of the observable universe is so large that light, travelling at the fastest possible speed, takes over 13 billion years to cross it. Second, we've learned about time. When we look out into space, we're looking back in time. The light from distant galaxies left those galaxies billions of years ago. We're seeing them as they were in the ancient past, not as they are today. In a very real sense, astronomy is a form of time travel. Every observation is a glimpse into history. Third, we've learned about mystery. Despite all we've discovered, the universe is still full of unknowns. What is dark matter? What is dark energy? How did the first galaxies form? Is there life elsewhere in the universe? What happened before the Big Bang? Does the universe have an edge, or does it go on forever? These questions remain unanswered, waiting for future generations of scientists to unravel. And finally, we've learned something about ourselves. We are part of this universe. The atoms in our bodies were forged in the hearts of stars. The carbon, nitrogen, oxygen, and all the other elements that make us who we are were created by nuclear fusion in stellar cores and scattered into space when those stars died. We are, quite literally, made of stardust. Our planet is a tiny speck in an incomprehensibly large cosmos. Our lives are brief flashes in the vast expanse of cosmic time. And yet, here we are, conscious, aware, able to look up at the night sky and wonder, able to build telescopes and spacecraft, able to piece together the story of the universe and our place within it. There's something profound about that. We live on a small world orbiting an ordinary star in an ordinary galaxy, but we have the capacity to understand the universe. We can trace the history of the cosmos from the Big Bang to the present. We can peer into the hearts of stars and probe the mysteries of black holes. We can search for life on distant planets and ask the deepest questions about existence. In many ways, we are the universe trying to understand itself. What comes next? As we conclude this journey, it's worth asking, what comes next? Where do we go from here, both literally and figuratively? In terms of exploration, humanity is just beginning. We've sent robotic probes throughout the solar system. We've landed on the Moon, Mars, Venus, Titan, and a few asteroids and comets. We've flown by every planet and even reached interstellar space with Voyager. But these are just the first steps. In the coming decades, we might send humans back to the Moon and then onward to Mars. We might build habitats on other worlds, learning to live beyond Earth. We might send more advanced probes to the moons of Jupiter and Saturn, searching for signs of life in their hidden oceans. We might even send a probe to another star system, though the journey would take decades or centuries. And with each new mission, each new discovery, we'll learn more. We'll refine our understanding of the universe. We'll answer some questions and raise new ones. In terms of understanding, we're also at an exciting frontier. New telescopes are revealing the universe in unprecedented detail. The James Webb Space Telescope, launched in 2021, is observing the earliest galaxies and studying the atmospheres of exoplanets. Future observatories will be even more powerful, capable of detecting faint signals from the most distant corners of the cosmos. We're building new experiments to search for dark matter and understand dark energy. We're developing better models of the early universe and how structures formed. We're using gravitational wave detectors to observe colliding black holes and neutron stars, opening up an entirely new way of studying the cosmos. And perhaps most exciting of all, we're searching for life. We're studying potentially habitable planets around other stars. We're exploring the icy moons of the outer solar system. We're listening for signals from alien civilizations with radio telescopes. It's possible that within our lifetimes, we'll find evidence that we're not alone in the universe. Or we might find that life is exceedingly rare, which would make our own existence even more precious and remarkable. Our journey to the edge of the universe has been a journey through space and time, but it's also raised some of the biggest questions we can ask. Why does the universe exist at all? Why is there something rather than nothing? This is perhaps the most fundamental question in all of philosophy and science, and it's one we may never be able to answer definitively. Why do the laws of physics have the form they do? The universe operates according to mathematical laws, gravity, electromagnetism, quantum mechanics. But why these laws? Why these particular constants and values? Some scientists think the answer might lie in the multiverse. If there are many universes, each with different laws and constants, then perhaps we live in one of the rare universes where the laws happen to allow for complexity, stars, planets, and life. This is called the anthropic principle. But it's controversial and far from proven. Is the universe finite or infinite? We know the observable universe is finite, but what about the universe beyond? This is still an open question. Both possibilities are mind-bending in their own ways. Will the universe last forever? Based on current observations, it seems the universe will continue expanding forever, driven by dark energy. Eventually, stars will burn out, galaxies will drift apart, and the universe will grow cold and dark. This is sometimes called the heat death of the universe, but there are uncertainties. We don't fully understand dark energy, and it's possible the future might hold surprises. And of course, there's the question of life. Are we alone? The universe contains billions of galaxies, each with billions of stars, and many of those stars have planets. It seems statistically likely that life has arisen elsewhere. But we have no definitive proof yet, and if life exists elsewhere, is any of it intelligent? Is any of it trying to communicate? These questions drive much of our exploration and observation efforts. At the end of our journey, standing metaphorically at the edge of the observable universe, looking back at everything we've seen, what's the appropriate response? For many people, including many scientists, the appropriate response is wonder, a sense of awe at the vastness, the beauty, the complexity of it all. The universe is more strange and magnificent than we could have imagined. There's also humility. We are small. Our planet is a tiny dot in an incomprehensibly large cosmos. Our civilization has existed for just a blink of an eye in cosmic time. And yet, despite our smallness, we matter. We have the capacity to understand, to appreciate, to care. We have the ability to look up at the stars and ask questions. And there's curiosity. The universe is full of mysteries waiting to be solved. Every answer we find leads to new questions. That's not frustrating, it's exciting. It means there's always more to discover, always more to learn. The universe doesn't owe us meaning. It doesn't exist for our benefit. But we can create meaning through our actions, our relationships, our pursuit of knowledge. We can look out at the cosmos and choose to explore it, to understand it, to protect the small corner of it we call home. After our epic journey, it's time to come home. We've travelled billions of light years, across billions of years of history. We've seen stars being born and dying. We've witnessed galaxies colliding. We've traced the threads of the cosmic web and touched the edge of the observable universe. But now, let's reverse course. Let's fall back through the cosmic web, past the superclusters and galaxy clusters. Let's zoom back through the Milky Way, past the galactic center, through the spiral arms, back to our little corner of the Orion Arm. There's our sun, a middle-aged yellow star among billions. And there, orbiting the sun, the planets, gas giants in the outer system, rocky worlds in the inner system, and there, the third planet from the sun, Earth. From space, Earth still looks like that precious blue marble. Clouds swirl over the oceans, continents are visible beneath, and somewhere down there, on the surface, is you, going about your day, living your life. It's easy to feel insignificant after a journey like this. How can we matter in a universe so vast? But consider this. You're part of the universe. You're not separate from it. You're made of atoms forged in stars. You're the result of billions of years of cosmic evolution. You're a way for the universe to know itself. And that's remarkable. Out of the chaos of the Big Bang, out of clouds of hydrogen and helium, emerged stars and planets. And on at least one planet, maybe more, emerged life. And that life evolved, becoming more complex over billions of years, until eventually it became conscious, aware, capable of looking up at the night sky and wondering what's out there. You are that consciousness. You are that awareness. You are the universe experiencing itself. So what have we learned from our epic journey to the edge of the universe? We've learned that the universe is vast beyond comprehension, that it's full of wonders, black holes, galaxies, nebulae, cosmic webs, that it's governed by laws we're still trying to understand, that it's full of mysteries, dark matter, dark energy, the nature of time and space itself. We've learned that we live in an extraordinary time. For the first time in human history, we can observe the early universe, detect gravitational waves, image black holes, discover thousands of planets around other stars. We're piecing together the cosmic story with unprecedented detail, and we've learned that despite the vastness of the universe, or perhaps because of it, our existence is precious. We live on a small planet, but it's the only home we've ever known. It's up to us to protect it, to cherish it, to ensure that future generations can continue to look up at the stars and wonder. The universe is calling to us. It's inviting us to explore, to discover, to understand. And we're answering that call. With every telescope we build, every spacecraft we launch, every question we ask, we're pushing the boundaries of what's possible. The edge of the universe, if it exists, is far beyond what we can reach. But the edge of our knowledge, that's something we can push. Every day, scientists and researchers around the world are working to understand a little bit more. And with each new discovery, the universe becomes a little less mysterious and a little more wonderful. So the next time you look up at the night sky, remember what's out there. Remember that every point of light is a star, potentially with its own system of planets. Remember that beyond what you can see with your eyes are billions of galaxies, each with billions of stars. Remember that you're looking back in time, seeing light that left those stars years, decades, or millions of years ago. Remember that you're part of something vast and beautiful. And remember that the journey to understand the universe, this epic journey to the edge of everything, is a journey we're all on together. Thank you for joining me on this voyage. Keep looking up. Keep asking questions, keep wondering, because in the end, that sense of wonder, that curiosity about the cosmos is one of the most human things we can do. It's what connects us to the stars and to each other. Until next time, clear skies and endless wonder.